Alright, I noticed that in the previous video that my face was kind of blocking out what you could see, so I apologize for that. And let's jump right into this. So, from before, from that formula, we know that Rigel appears 1.28 times brighter than Betelgeuse, but Rigel is 1.6 times further away than Betelgeuse. So, what we can infer from there is Rigel is actually intrinsically 3.3 times brighter than Betelgeuse because of the distance difference. To characterize a star's intrinsic brightness, let's look at the definition of absolute magnitude over here. So this is what we use to determine absolute magnitude, the symbol capital M sub V. Absolute magnitude then is a magnitude that a star would have if it were at a distance of 10 parsecs away, or about 32.6 light years away from us. I think I was previously saying 10 light years to you guys as a class, but it's actually 10 parsecs. Alright, let's go back to this one. Okay, so let's look at our example now of Betelgeuse and Rigel again. Let's take a look at the intrinsic brightness, or little m sub v, of Betelgeuse versus Rigel. Okay, that's the brightness that they appear to have to an observer on Earth. The absolute magnitude, so if we were able to get closer to these stars and have each of them be 10 parsecs away from us, Betelgeuse would be negative 5.5 and Rigel would be negative 6.8. Remember that a lower number is a brighter star. The real distance of Betelgeuse is about 152 parsecs away, and Rigel is about 244 parsecs away. So the differences in luminosity gives us a ratio. So we can raise this luminosity ratio to the 1.3 power, and we get this number 3.3 for our luminosity ratio. Now, if we know a star's absolute magnitude, we can infer its distance by comparing absolute versus apparent magnitude. And you don't have to worry about the math over here. What I just want you to know is how to use this table. If m sub v minus big M sub v is equal to 0, then we're at a distance of 10 parsecs. Does that make sense? If its intrinsic brightness is equal to its absolute magnitude, then we're at a distance of 10 parsecs away. This is kind of an ingenious method, I thought. If the difference between the two is 1, then we're 16 parsecs away. We just use that ratio that we had earlier. So the absolute magnitude subtracted from the intrinsic magnitude, or the difference between the absolute and the intrinsic magnitude, can give us a distance estimation. I thought that was a pretty cool trick. Trick of math. Alright, now we also know the Stefan-Boltzmann law. We've looked at this before. We know that the flux increases with surface temperature. So hotter stars are brighter, but brightness also increases with size. Wien's law. Absolute brightness is proportional to the radius squared. Remember this formula. You don't have to know how to use that formula. But just remember, if you see that, you should automatically be thinking Stefan-Boltzmann, and you should be thinking raising the temperature or increasing the size of the star will make it brighter. Okay, let's look at an example. Our North Star, Polaris, is an example of this. Let me get to it. Okay, Polaris has just about the same spectral type and thus surface temperature as our Sun. It's an O class star. But it's 10,000 times brighter than our Sun. So What do we know from that? We know that Polaris is about 100 times larger than the Sun. And this causes its luminosity to be 10,000 times, or 100 squared, more than our Sun's luminosity. It's brilliant how they did all this stuff. I love it. Right, we have done the Hertzsprung-Russell diagram. You should be super excited about that by now, because you know how to use this. You know that luminosity increases as you go up the y-axis. You know that temperature decreases as you go from left to right on the x-axis. And temperature relates to its spectral class. We remember, oh, be a fine girl, guy, kiss me. Right? So these are spectral class, and then wherever you plot the star is the Hertzsprung-Russell diagram. Just a quick review of that. Most stars are found along this area right here. That's right, the main sequence. Our Sun is one of those main sequence stars. Then we have others right here. Let me think. Let me look at my notes real quick. Yeah, up here we have the blue giants and blue supergiants. Over here, the red supergiants, red giants, and down here, white dwarfs. And we call these, clear down here in this corner, the red dwarfs. That's something that I wanted to mention that we haven't mentioned yet in our discussions. Okay, now, notice, if we draw a line down here, all of these stars would be, on this line, would have the same temperature. These stars up here are much brighter than main sequence stars, so what must be true? And the answer is already given away, but the thing that must be true is that they must be much larger than main sequence stars. So we call those giants. Down here, same temperature, again, as these stars right here. They're much fainter, so they must be much smaller. They must be dwarfs. We call those stars dwarf stars. Another thing the Hertzsprung-Russell diagram can tell us is the size, the radius of the star. These lines represent how many sun radii they are. So everything along this line right here is the same size as the Sun. If we jump up to this line, it's 10 times as big as the Sun. And this line, 100 times bigger than the Sun. It's radius. Okay, you get the point. If we go below that line, then these are 1/10 the size of the Sun. Okay, these white dwarfs on average are 100 times smaller than the Sun. Very small stars. And here you can see some examples of our familiar ones: Rigel, Betelgeuse, Polaris, and our Sun. Okay, let's see on my notes over here. Back to here. So let's add another way to classify stars. We know spectral class. Stars also have luminosity classes. So anything on this line, and hopefully you're writing this down right here, anything on this line are called bright supergiants, or we call them luminosity class 1A. Anything on this line, we call them supergiants, or luminosity class 1B. Sorry, it's late and I can't pronounce things. Anything on this line, bright giants, or luminosity class 2. Anything here, giants, or luminosity class 3. Anything on this line, subgiants, or luminosity class 4. And anything on here, main sequence stars, or luminosity class 5. So you can put those together, like with our Sun. You can add G2 with 5. So our Sun is a spectral type G2 and a luminosity class of 5. Polaris would then be what? Polaris is up here. So Polaris would be spectral class O. No, I'm sorry, G, just like our Sun, G2. But it would be in the luminosity class 1B because it's close to that 1b line in that group right there. Okay, now if we look at the spectral lines of giants, pressure and density in their atmosphere are lower than in the main sequence stars. So the absorption lines of giants and supergiants are narrower than the main sequence stars. So if we look at main sequence stars, look how wide those spectral lines are compared to the spectral lines of giants. And then this pencil thin line right here is the spectral line of a supergiant. Okay, again, this is because pressure and density in the atmosphere of giants is lower, and so we get thinner lines. Pressure and density in main sequences are higher, and so we get these thicker lines. Let's talk about this. You can estimate the distance of a star using what's called the spectroscopic parallax. Let's take a look at what that is. Let me get to my notes real quick. I just drew a blank on this spectroscopic parallax. It'll come back to me. We'll get back to that in just a second. Okay, let me go to binary stars then. More than 50% of all stars in our Milky Way are binary stars, like I said earlier. So they orbit each other, or rather, they orbit a center of mass of each other. And if we can understand, or if we can measure and understand their orbital motion, we can estimate their mass. So let's take a look at some examples here. Imagine their center of mass is like a seesaw. If you have a friend that's about the same size of you, you would balance each other out on a seesaw. But if you had a friend that was much more massive than you, if you put them on the end, that would tip the seesaw up. In order to balance it, your friend has to move closer to the fulcrum. So the more unequal the masses are, the more the larger star is shifted toward the center of mass. Sometimes these stars are so much more, so much bigger, or so much more larger than these stars that the center of mass is somewhere inside that mass, that sun, rather, that star. I'm going to skip this next slide, and let's go back real quick to Kepler's law. Remember that Kepler's law is equal to the period in years squared is equal to the astronomical units cubed. Okay, this is only valid for the solar system where the star has at least one solar mass in the middle. We find that this same law for binary stars with masses, mass A and mass B, different from one solar mass, so this number added together has to be different than 1, is equal to astronomical unit and period squared. Astronomical units cubed. Separation, this would be the separation between those two stars, and the period squared. So here's an example of that. Let me go back here. Way to estimate mass. So the combined mass of these stars is equal to their period in years cubed. I'm sorry, this is not their period cubed. This is their distance away from each other cubed over their period squared. So 16 cubed over 32 squares is equal to 4 solar masses. So we know the combined mass of this binary system is 4 solar masses. Any binary system with a combination of period and separation that obeys Kepler's law must have a total mass of 1 solar mass. I think I might be able to fit one more slide in before I have to pause. Actually, I don't think I am. So I will pause here. You guys will see me right away, and I will be back in just a little bit.